It's another session to learn and understand calculus. Are you ready with your materials for your math class? You might want to print out Learning Worksheet 6. A notebook or paper for solving and taking down important points will be helpful as we discuss a new lesson. Settle down and we will proceed with the topic. Definite integral. In our discussion of calculus, we've been analyzing functions using their graphs, table of values, and equations. We've learned to use limits as a tool to analyze the behavior of the dependent variable as the independent variable approaches a specific value. We've also looked into the rate of change of certain values, which we referred to as the derivative of a function. We applied the concept of limits in finding the derivatives. In the last part of the course, we are learning about integrals, which still requires us to make use of our knowledge of derivatives. One of the applications we will encounter is using integrals to find the area under the curve. Can you think of a way on how to find the area of this region? Based on our knowledge of area, we can divide this region into portions that are familiar to us. For example, we can consider rectangles. If that region is within the closed interval AB, then for each rectangle, the height is equal to the function value. And if we consider n rectangles, then each rectangle will have a width of b minus a over n. This width, which is measured along the horizontal, can be referred to as the change in x. Putting all these rectangles together will give us an approximation of the area under the curve. We refer to this as the Riemann sum. Is it possible to have a closer approximation or even an exact value of the area? If we consider more rectangles, thus n gets bigger, then we can find the area under the curve by finding the limit of the Riemann sum as n approaches positive infinity. Note that the change of x is also referred to as dx in our lesson on derivatives and integrals. The limit of the sum of the areas of the rectangles is defined as the definite integral. This is written using this notation. Before we discuss examples on evaluating definite integrals, let us look into some properties which will help us in our solutions. Since a definite integral refers to the area within the interval a to b, this first property tells us that there is no such area. Next, like in finding the antiderivative of a function and applying the reverse of the rules on differentiation, then we can factor out the constant c. In this property, if we're finding the definite integral of the sum or difference of two or more functions within the interval AB, then it is the same as finding the sum or difference of the definite integral of each of the functions within the interval AB. Here, if the bounds of the interval are reversed, then the result is the negative of the definite integral. Lastly, if f is a continuous function on a closed and bounded interval containing the numbers a, b, and c, then the definite integral from a to b plus the definite integral from b to c is equal to the definite integral from a to c. Another important tool in finding the definite integral is the fundamental theorem of calculus. If f is continuous on the closed interval ab, then the definite integral of f from a to b is equal to the function value of the antiderivative when x is equal to b minus the function value of the antiderivative when x is equal to a. Let us try to apply these in our first example. Find the definite integral of 7 minus 3x from 0 to 2. We first find the antiderivative, which is equal to 7x minus 3 halves x squared. Given this, we apply the fundamental theorem of calculus by evaluating the antiderivative when x is equal to 2 and when x is equal to 0. Simplifying, the definite integral is equal to 8. These properties may also be applied given a trigonometric function. In this definite integral, we know that the antiderivative of cosine x is sine x. So we find sine pi over 2 minus sine of negative pi over 2. It is equal to 1 minus negative 1 or 2. In our last example, we first find the antiderivative of x times the square root of quantity 1 minus x. We recognize that this will require substitution. Let s be equal to 1 minus x, thus replacing the radicand. To replace the remaining variable x, we express x as 1 minus s. With these representations, we find that dx is equal to negative ds. Expressing the original function in terms of s, we now find the antiderivative of quantity 1 minus s times the square root of s times negative ds. This is the same as the quantity s minus 1 times s raised to 1/2 ds. Simplifying, we are finding the antiderivative of s raised to 3/2 minus s raised to 1/2 ds. Applying antidifferentiation, we obtain s raised to 5/2 over 5/2 minus s raised to 3/2 over 3/2 plus the constant c. Rewriting the complex fractions, we obtain 2/5 s raised to 5/2 minus 2/3 s raised to 3/2. Rewriting this antiderivative in terms of x, we have 2/5 times the quantity 1 minus x raised to 5/2 minus 2/3 times quantity 1 minus x raised to 3/2. Which we need to evaluate when x is 1 and when x is 0. Applying the fundamental theorem of calculus gives us the definite integral equals 4 over 50. Note that all these values obtained represent the area bounded by the graph of the function, the x-axis, and the lines x equals a and x equals b. More examples are discussed in the textbook and Learning Worksheet 6. Kindly answer the exercises as practice on finding the definite integral.